Okay, so we're on to section 1.3 called two-dimensional motion. I think the best way to describe this is that objects just don't move in straight lines forward and backwards. You think about when you're walking on a floor in a gym. Not just forward and backwards, it's left and right and combinations of both as you move at an angle. And that's what we want to study. And the best way to look at it is through an example. So here's our example. A bunny hops 3 meters east in 3 seconds. Then the bunny stops for a second. Then the bunny hops 4 meters south in 4 seconds. Draw a diagram of the motion. Okay, so first thing you have to do is establish a direction. So I draw this arrow here. Draw this arrow here saying to everyone that's reading my work that direction's north. Then I mark a dot and I call that initial position, DI. And that's where I start from. So 3 meters east, stops for a second, 4 meters south, then I draw a dot and I label that uh, final position. Then what I do is I draw an arrow from initial position to final position. Let me finish the arrowhead there. There it is. And I call that delta D, or change in position displacement, because it's telling the reader of your work, look, the object started here and now it is in this new position. So this is showing how far apart the two positions are, and it's also showing a direction. It's not just saying I'm so many meters away from where I started. Follow along the arrow here. It'll show you the direction and how far away you are from where you started. Your position has changed. Displacement, change in position, and it's represented by this arrow, this vector. Now, when we're showing direction, a lot of times it's useful to use an angle. And the angle would be right in here between the 3 meters east and the displacement. And the letter that they usually use is the Greek letter theta. Now, there are some things that we want to calculate here. And what we want to calculate is the distance, d, that the object traveled, bunny in this case, bunny rabbit hopping, and the average speed. So the way we do that is we find the distance it traveled by finding this here. What is the distance it traveled during its first motion? So we represent that by these two lines, and in between the lines we put the first displacement, displacement number 1. But when you put these two lines on it, it's basically saying, look, all I want is the magnitude of this vector. I'm going to ignore the direction. So when you see a vector with two lines on each side like this, that's saying just the magnitude of the vector. So that's what the distance is. It's the magnitude of the first motion, 3 meters east, the magnitude of the first displacement, plus the magnitude of the second displacement. So it would be the magnitude of 3 meters east plus the magnitude of 4 meters south. I don't care about the direction. I just want to take the 3 meters from there, the 4 meters from there, I add them together, and I get 7 meters. So the distance that the bunny hopped is 3 plus 4 is 7. Next, I want to calculate the average speed. Well, the average speed is by the equation that you should have in your equation sheet, the distance divided by the time. So 7 meters divided by 8 seconds, they each have two significant digits, so my answer would be 0.88 meters per second. Now, does that mean that during the entire motion, the object moved at 0.88 meters per second? No, it's an average. We don't know how the bunny moved. It could have been fast and slow, fast and slow, fast and slow. We know it stopped here for a second. And then fast, slow, fast, slow. I don't know. We don't know. We're not told. So all we can calculate are the averages. So we've taken a look at this, and we've taken a scalar look at the motion because we've found distance and average speed. The next thing we want to do is take a look at this motion and describe it with vectors. And the vectors that we want to use to describe the motion are twofold. There's the displacement, and there's the average velocity. Now remember, these are vectors. So the vector will have a magnitude to it and a direction. So we want to find the magnitude of the displacement first and its direction. Well, look, this is a right angle triangle. This is our old friend Pythagoras. If I want to find the magnitude of this, I just use the Pythagorean theorem. If I want to find this angle theta in here, I can use some trigonometric functions. And then I will be able to find the displacement of the bunny rabbit. Let's try it. So here we go. Displacement. I need to find the magnitude and the direction. So to find the magnitude, I use the Pythagorean theorem and I get 5 meters. To find the direction, I use tan inverse, which is opposite over adjacent. So if you take a quick look here, let's go back. Opposite to this angle, 4 meters. Adjacent to the angle, 3 meters. And I get it to be 53 degrees. When I combine the two, I get that the displacement is 5 meters. And this is how I write it. Listen to me carefully. 53 degrees south of east. It's giving a direction. Displacement is a vector. So what it's saying is, look, this direction here is east, but the direction of the displacement is 53 degrees away from that easterly direction. And it's 53 degrees towards the south. You've shifted towards the south from the east. So you say 53 degrees south of east. And now you brought the magnitude calculation and the direction calculation back together, and we get 5 meters per second, 53 degrees south of east, which literally means the new position is 5 meters away from the initial position at an angle of 53 degrees south of east. It's just not 5 meters away. 5 meters away could be in any direction. It's in a particular direction, the direction that you calculated. Next, average velocity now. It's a vector. Displacement over time. So we take the 5 meters, 53 degrees south of east, we divide it by the 8 seconds, the total time. Some of you might think it's 7 seconds because it paused for that 1 second when it made a directional change. No, you take into account that second. It's the total time. And following the rules of significant digits, we divide 5 meters by 8 seconds, and we get 0.62 meters per second, and the direction carries through. Next, now the second part of section 1.3 is what we call relative motion, relative velocity. And it's based upon this principle right here. It's based upon the principle that the motion of an object is described, and that's spelled wrong, ignore that L, let me fix that. There, gone. It's described with respect to a point of view, or what a physicist, a scientist would call a reference frame. Let me give you an example. If we were in a class together, I would say, Mr. Zafiro is walking while throwing a ball. So what I would do in front of the class, me, I would throw a ball straight up and down as I was walking from one end of the classroom to the other. And to me, the motion of the ball would be straight up, straight down, straight up, straight down. But to you who are sitting in your seats, you would see the motion of the ball to be a parabola. Try this at home with a friend. You throw a ball straight up and down while you're walking, and let a friend observe. Then switch places and see what happens. I've also included some videos that really show what relative motion means in the announcement associated with this work. Now, here's an example. Here is a car, and we're going to label this car A, and there's a person in the car. Now, that is a point of view. It is a reference frame. One of the reference frame is observing the world while you are in moving car called A. Here is another car. We'll label this car B, sports car, okay? And it is a reference frame. It is a point of view. You're observing the world while you're in car B driving around. So you see motion from your point of view. And then the other reference frame is the ground. Some person just standing at the side of the road, not moving. So they're not moving with respect to the ground. So we call that the ground reference frame. So the velocity of car A with respect to the ground, what ground person sees is that car A is moving at 10 kilometers per hour east. We're making this direction east. And the person here at the ground sees that the car B is moving at 10 kilometers per hour west. Okay? Now, let's change this around. What is the velocity of the ground with respect to the person in car A? Have you ever been in a car and you're not the driver and you're looking at the side of the road, or you're looking at the background, the trees, the houses as you're driving by? Doesn't it look like they're moving backwards? Yeah, it does. So that means these two are opposites of each other. If the velocity of the car A with respect to the ground is 10 kilometers per hour east, the velocity of the ground with respect to the car is negative 10 kilometers per hour east. Similarly, if the velocity of car B with respect to the ground is 10 kilometers per hour west, then the velocity of the ground from a person in car B is negative 10 kilometers per hour west. It looks as if the ground is moving backwards. And the general equation for that is right here, and I would add this to my equation sheet. Velocity of A with respect to B is equal in magnitude but opposite in direction to the velocity of B to A. That's an equation to put in our equation sheet. There, if you switch the reference frames, the vectors switch direction. Now here's another question I just want to ask you to calculate using your common sense. Just common sense. What is the velocity of car A with respect to the person in B? So here's this person in car B, and they're watching car A as the car approaches them. Well, if you think about it, both cars are moving, so the distance between them is going to really reduce quite quickly because they're both moving. So you would add the two velocities, and you would say that the velocity of car A with respect to B is 20 kilometers per hour east. Car A is really moving quickly towards car B because they're both moving. Or if you don't want to write it as 20 kilometers per hour east, you can write it as negative 20 kilometers per hour west, because the 20 kilometers per hour west, because the negative of west is east. Similarly, what is the velocity of car B with respect to the person in car A? So you're sitting here in car A and you're watching B come towards you. Well, since you're both moving at 10 kilometers an hour, the velocity of B with respect to A would be 20 kilometers per hour west. Or if you want, negative 20 kilometers per hour east. They're moving towards each other. Now there is an equation that lets you solve this. And the equation is the velocity of A with respect to B is equal to the velocity of A with respect to G plus the velocity of G with respect to B. So you add them together like so. A to G, right? We know what that is. A to G. We calculated it, 10 kilometers per hour east. What's G to B? Ground to B, right here. Negative 10 kilometers per hour west. Or if you want 10 kilometers per hour east, negative west is east. So I put that in there and I get the right answer, 10 kilometers per hour east. So if you ever want to add vectors, there's a rule you have to follow. If you ever want to add vectors for relative motion, the rule that you have to follow is that you have the velocity of A to B is equal to, if there's an A as the first letter here, the first letter here has to be an A. If there's a B as the second letter there, B has to be the second letter in the second one. And then the interior has to be the same reference frame. In this case, it's G. So generally speaking, we can come up with a general equation, and here it is. Velocity A to B is equal to velocity A to X. Oops, don't want to do that. Plus velocity X to B. First, second, and then a common one in between. Let's do an example. Let's say here is a float, some type of parade. I don't know if we're having parades anymore, but let's pretend. And let's say that the float is one of the reference frames. Okay. And right here is a person on the float, and they're throwing a ball. And that's another reference frame. And then the float itself is moving on the ground, and that's another reference frame. So Let's say that the ball is being thrown by someone on the float. So the velocity of the ball, if it's being observed from someone on the float, is positive 10 kilometers per hour. So there's the ball. Boom, it's moving at positive 10 kilometers per hour. The ball being observed from the float reference frame. Now, how fast is the float moving on the ground, the road, what have you? Well, let's say that the float is moving with respect to the ground at 2 kilometers per hour. So you would use this general equation, it's just a different version of it. X first, X first. Y last, and we need a common reference frame to link them. So if I'm going to do this, I say the velocity of the ball with respect to the ground, ball first, ball first. Ground last, ground last. Let me make that a better G. And I need a linking frame. In this case, the linking frame is the float. So velocity of the ball with respect to the ground, the velocity of the ball with respect to the ground is equal to the velocity of the ball with respect to the float plus the velocity of the float with respect to the ground. That's how we add them. So that would be 10 plus 2 gives me 12. I have to have positive signs here. Look, I put a positive sign there, a positive sign there, a positive sign there because it's a vector. It's a vector. It's a vector. I just can't write 2 kilometers per hour. That would be a scalar. There's no direction. So please keep that in mind. Okay? So here's another classic example. This is a river. So the river is water. So one of the reference frames is water. So one of the reference frames would be a particle of water as it's moving. So it's a moving reference frame there. Another reference frame would be this little man in the boat here. That would be a reference frame, observing the world as you move in this boat. Another reference frame would just be some person sitting at the side of the road, on the ground here, side of the river, I should say, watching this all happen. So let's establish a direction. This here is north. Okay, straight up the page. Here's the river. The river's got a current. So another way of describing current, if you were a physicist, is you would say current can mathematically be written as the velocity of the water with respect to the ground, which makes sense. How fast is the water moving past us when we're watching it from the ground, from the riverbank? And in this case, it's 10 kilometers per hour east. Now, what is the velocity of the boat with respect to the water? Well, the velocity of the boat with respect to the water here, I'm told that the boat is aiming itself with its motors pushing it along north. It's aimed north. So it's moving in the water, careful what I said there, in the water at 5 kilometers per hour north. So it's moving in water, which the water itself is also moving. But if you only look at it in terms of how fast is it moving in the water, it's 5 kilometers per hour north. Velocity of the boat with respect to the water. So here, I want to calculate what is the velocity of the boat with respect to the ground. What's the person here observing with this person moving in the boat? Well, do you think the person's going to go straight across if the river's got a current? I don't think so. The person is going to move with the boat still pointing north, but the boat's going to move at an angle because the engine is pushing it forward, but the river current, the velocity of water with respect to the ground, is pushing it to the side. So it's actually going to have a velocity at an angle. And that would be the velocity of the boat with respect to the ground. So that means I have to take the velocity of the boat with respect to the water and add it to the velocity of the water with respect to the ground. Remember, there's a rule we follow here. First one here, first one here. Last one has to be the last one. And then you need to have a reference frame that connects them. In this case, it's water. So I add them. Okay, 5 kilometers per hour north plus 10 kilometers per hour east. Well, what would that be? 15 kilometers per hour northeast? I wish it was that simple. It's not. We have to add vectors in a way that's called vector tip to tail addition. That's how you add vectors. We actually did it with the bunny rabbit. I just didn't give you the name at that point. We were adding displacement vectors at that point. Here we're adding velocity vectors, but the method is the same. It's vector tip to tail addition. And this is what we do. We put a starting point here. We label that start, and we say, let's put the velocity of the boat with respect to the water. Let's draw that vector. So I'm going to draw that vector, 5 kilometers per hour north. It's in purple here. I draw it. What next? I want to add to that vector. How do I add to a vector? I go tip to tail. So the tip of the first vector must be connected to the tail of the second one. And I draw the second vector, which is velocity of the water with respect to the ground. There it is, 10 kilometers per hour east. I draw that. And I call that the end point. Then I draw an arrow connecting the two. And the arrow connecting the two is a representation of the velocity of the boat with respect to the ground, VBG. Now this is a vector. So a vector has the magnitude part and the direction part. So since this is a right angle triangle, we can use my friend and yours, the Pythagorean theorem, to find the magnitude. Remember, when you have these lines around a vector, it means magnitude. So that's what I do. I use Pythagoras. The magnitude of the velocity of the boat with respect to the ground is I take the 5 kilometers per hour, square it, 10 kilometers per hour, square it, add them up, then square root, I get 11.2 kilometers per hour. Now I want to find this angle theta. Now I strongly recommend you always put the angle theta near the start point. I don't recommend putting it there. The textbook does it from time to time. I recommend putting it right there. I recommend putting it right there. So I use tan inverse, opposite over adjacent, 10 over 5, I get 63 degrees. Now I take the magnitude part of the vector, the direction part of the vector, I bring them together, and I get the final answer. The velocity of the boat with respect to the ground is 11.2 kilometers per hour in a direction 63 degrees east of north. 63 degrees east of north. And I can, oopsie, let me draw that better. I don't like that at all. Not one bit. Nope, let me draw that better. Here we go. So here's north. Here's east. Here is the vector that we just found. It's 63 degrees east of north. So that's 63 degrees east of north. Okay. So I hope you can figure out from math class that there's another angle down here that if you add to the 63, if you add this angle to the 63, you'll get the full 90. Those types of angles are called complementary angles. And so you have to add 27 degrees to the 63 to get to 90. Okay, to get the 90. So if you wanted, you could rewrite this as 27 degrees north of east. If you wanted, both are acceptable. So let's say we want to find out how far this actually moves in a certain amount of time. We want to find its displacement, the displacement of the boat with respect to the water. We want to find it. Okay, so the velocity of the boat with respect to the water is equal to the displacement of the boat with respect to the water over time. Remember we had that equation? Velocity is displacement over time. Now for the sake of this question, let's say the boat moved for 2 hours. I just came up with a number. So I rearrange this equation right here. Now some of you may want a triangle. You can do little triangles for all these. Okay, so it would be displacement over time, and this would be velocity. So if you want to find velocity, you cover it up and you're left with displacement over time. If you want to find displacement, you cover it up and you're left with these two multiplying each other, and that's what I have here. So I put in the velocity that I calculated from the previous page. I put in this 2 hour, this arbitrary time that we're just using for this example, and 2 times 11.2 is 22.4. The hours cancel, so it's just kilometers, it's a displacement, and we carry the angle through. And that's how we would calculate the displacement. Now, I got another question for you. I want you to think about this. If I have no current, this will go straight across like that. If I have a weak current, it'll go across at an angle. If I have a strong current, the boat would probably move like this. I'd like you to think about how much time it takes to cross the river if there's no current, how much time it takes to cross the river if there's a slow current, and how much time it takes to cross the river if there's a very fast current. How would these three times compare? Think about that, because the answer is, dramatic pause, all three times would be the same. Thanks, bye.